In this section, we will look at how to carry out a hypothesis test using the Poisson distribution. The number of errors in a textbook can be modelled using a Poisson distribution. The author of the textbook claims that there is a chance of 1 error in every 4 pages. After working through the textbook, the first 10 pages you find 6 errors. Would this be enough for you to doubt the author's claim? So we're going to take the number of errors in the textbook as a random variable. Now, the author's claim is that there is an error, 1 error in every 4 pages. That gives us a rate of 1/4 or 0.25. So as a Poisson distribution, if you have read 10 pages, then the rate you would use would be 10 multiplied by 0.25. Or x is modelled by the Poisson distribution of 2.5. This is equivalent to saying that there is a rate of approximately 2.5 errors in every 10 pages. We have observed that there are 6 errors. Now 6 is more than 2.5. We want to know what the chances are of this occurring randomly in this Poisson distribution. So we're going to calculate the probability of there being 6 or more errors in 10 pages using this rate here. So the probability that x is greater than or equal to 6, we need to convert that into a less than or equal to problem. So this is the same as 1 minus the probability x is less than or equal to 5. This gives us 0.042 or approximately 4.2%. Is this a low enough percentage to doubt the advertiser's claim of 1 error in every 4 pages? Well, if you were using a significance level of 4.2%, yes, this result would be significant. Some information about hypothesis testing in general. A statistical hypothesis test is used to check an assumption about a population parameter, which we're going to call A. The null hypothesis refers to the population parameter that is being tested. The null hypothesis is denoted by H0 and is usually written as P equals A, where A is the probability that is currently being assumed. The alternative hypothesis refers to a region of values that allows you to either accept or reject the null hypothesis. The alternative hypothesis has 3 possible outcomes. If you think that the null hypothesis is too high, then you can propose an alternative hypothesis, H1, that P is less than A. If you think the null hypothesis is too low, then you can propose an alternative hypothesis, H1, that P is greater than A. And if you suspect that the null hypothesis is wrong, but you're not sure whether it's too high or too low, then the alternative hypothesis would be that P does not equal A. So all of the null hypotheses are all denoted as H0. The first 2 are one-tailed tests. This is because you would only be checking one side of the null hypothesis. The third type is a two-tailed test, as you'll be checking both sides of the null hypothesis. The significance level of the test is given at the start and is normally denoted by alpha. Typical significance levels are often 1%, 5% or 10%. You would then calculate a p-value based on your observations. So you would take a sample and you would calculate the probability of that occurring under the distribution that you are testing under the null hypothesis. You would then compare the p-value you had calculated with the significance level to decide whether you had any evidence to reject the null hypothesis. If you calculate a p-value that is lower than the significance level, you would conclude that you did have sufficient evidence to reject the null hypothesis. For example, if you had chosen a significance level of 0.05 and you'd calculated a p-value of 0.04, you would say that this was sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. However, if you calculate a p-value that is greater than the significance level, then you would not have sufficient evidence to reject the null hypothesis, so you'd accept it. If you choose a high significance level, you're more likely to reject the null hypothesis. However, it's more likely that you would be incorrect in doing this. In other words, you would be rejecting the null hypothesis even though it was correct. Conversely, if you choose a low significance level, it's more likely that you will accept the null hypothesis. Typical significance levels are often 10, 5 or 1%. And if you were taking a two-tailed test, you would need to test the p-value against half of the significance level. So if you were choosing a significance level of 0.05, you would have to check it, compare it with 0.025. A hypothesis test for the Poisson distribution follows the following steps. First, you define what the population parameter is for the mean. This means give a sentence explaining what it is in the context of the question. For example, in the textbook example, we would say lambda is the mean number of errors in 10 pages of the textbook. You must be very clear in this. Just to say lambda is the mean number of errors would not be enough. You would need to clarify that you were looking at 10 pages of the textbook. You would then state the null hypothesis, the alternative hypothesis, and the significance level for your test. So in this example, the null hypothesis H0 was that lambda was 2.5. This was because there was a rate of one error in every 4 pages, 0.25, and we were looking at 10 pages. The alternative hypothesis for a one-tailed test would be that lambda was greater than 2.5. We would test this at a significance level of 5% or 0.05. We then state what the population distribution is and the test statistic. So X is being modelled as a Poisson distribution with a rate of 2.5, and X is the number of errors in 10 pages of the textbook. So this part at the end is you explaining what you have observed. You have observed some errors in 10 pages of the textbook. At this point, we haven't actually written down what we observed, which was 6 errors. We've just said that X is the number of errors that we are looking for. We then use the observed value of 6 errors to calculate a p-value. So because we have observed that 6 is more than the average rate of 2.5, we're going to calculate the probability of X being greater than or equal to 6. We did this and calculated 0.04202. We then compare this with the significance level. 0.04202 is less than 0.05. So because this is less than the significance level, we can say that there is sufficient evidence to suggest that the mean number of errors is greater. So in other words, there is sufficient evidence to suggest that we reject the null hypothesis. Remember that these conclusions must not be absolute. We can only claim that there is sufficient evidence. We cannot claim that something is definitely correct or definitely incorrect. In this example, we have a 3-star restaurant that serves an average number of 32 customers in a working day. It is then upgraded to a 4-star restaurant and serves 184 customers in 5 working days. So the observed value is 184 customers in 5 days. We want to check at a 5% significance level whether this upgraded star rating has changed the number of customers. So because we just suspect that the number of customers has changed, but we're not stating whether it has increased or decreased, this will be a two-tailed test. So first we must define the population parameter for the mean. Now we are considering the rate over 5 working days. So lambda is the mean number of customers over a working week of 5 days. We're now going to state the null and alternative hypothesis and the significance level. So the null hypothesis, if the average number of customers was 32 customers in a day and we are considering 5 days, we need to multiply 32 by 5 to give us H0 is that lambda is 160. That's 32 times 5. The alternative hypothesis is that lambda is not equal to 160, but at this stage we are not saying it will be higher or lower. We're going to use a 5% significance level, 0.05. Because we're going to be doing a two-tailed test, when we have calculated our p-value, we will be comparing to half of the significance level, so 2.5%. We're now going to state the population distribution and the test statistic. So the population distribution is that X is modelled with a Poisson distribution with a rate of 160. This is from the null hypothesis. And X is being defined as how many customers we have observed in a working week. So X will be this here, this 184. We're now going to calculate the probability using our single observation. So using a Poisson distribution with a rate of 160, we are going to calculate the probability of seeing more than or equal to 184 customers. The reason we are choosing greater than or equal to is because we have observed a value that is higher than the rate we are using. If we observed a value that was lower, we'll be using less than or equal to here. So to calculate this, we need to do 1 minus the probability X is less than or equal to 183. This gives us 0.0341. We're going to compare this with the significance level, remembering that we need to divide the significance level by 2 because it's a two-tailed test. So we're going to compare to 0.025. The p-value we have calculated is greater than this value. This means that there is not sufficient evidence to suggest that we reject the null hypothesis. So the sufficient evidence is that we should accept the null hypothesis because the rating does not seem to have significantly changed the mean number of customers. Now complete exercise 2B on page 26.